Sorry, I hit a wrong button. So I want to go back. So there's question 66. I'm going to move up to question 67 here. 67 has Superwoman hovering above the ground, and she's going to try and save somebody who is free falling at a terminal velocity of 140 kilometers per hour. Remember what I said in yesterday's note, that when a person is falling, if we ignore air resistance, the person will continue to speed up. But if we, in the real world, there is air resistance. So what that means is at some point, the downward force of gravity will be offset by the upward force of air resistance pushing back on that person, and they will reach constant speed. And they will continue to fall at constant speed once they have reached that terminal velocity. In this case, it's 140 kilometers an hour. Okay, so the question says, Superwoman is hovering above the ground when a person goes free falling by her at 140 kilometers an hour. Okay, so let's draw a picture. Here's Superwoman. Whoops. There's her cape. And here's a person that's going to go free falling past her at a constant speed of 140 kilometers per hour. Okay, let's go back to our question. Unfortunately, that person's parachute does not open, and Superwoman is there. It takes Superwoman 1.9 seconds to realize that the person is going to be in trouble. Okay, so in 1.9 seconds, what's going to happen? This person is going to get, hopefully not to the ground, that person's going to get to here. So between here and here is 1.9 seconds. Now Superwoman sees what's going on, and she's going to have to scoot down to pick up that person before they go splat, right, on the sidewalk. So it says, what must her acceleration be if she is going to catch the parachutist before she hits the ground, which is 1,000 meters below? Okay, so here's our picture. The distance from Superwoman to the ground is 1,000 meters. Now, what I know is a couple of things. She's going to come swooping down and save the day, right? She's going to collect this person when they are, let's say, 1 meter above the ground, right? Just before impact, Superwoman's going to scoop in and save the day. Now, the question is, what is her rate of acceleration? Now, I know a couple of things, right? Let's go back to the picture. I'm going to make this picture a little bit bigger. Okay, so what I know is there's two distances for my free faller here. There's the distance that he or she falls between here and here, and then there's another distance between here and here. So I can calculate this distance in here because I know the speed and the time. So the speed at 140 kilometers per hour, I'm going to switch it to meters per second. 1,000 meters is 1 kilometer, and 1 hour is 3,600 seconds. So her speed is 140 divided by 3.6. And she's traveling at 38.9 meters per second. So I can find the distance that she travels in here by using my speed times time formula, which is 38.9, which is still on my calculator, times the 1.9 seconds. And I'm getting 74 meters. Okay, so if I know that's 74 meters, I can calculate this distance in here because it's going to be the 999 that's going to keep her from hitting the cement minus the 74 that she's already traveled. So it's 925 meters. Okay, so in 74 meters, in 1.9 seconds, the person falls to here. My picture's not to scale, obviously. By the time the person gets to here, Superwoman realizes that this person is now here and is going to go splat in another 925 meters. Right, so what I need to figure out is if this person is going to fall another 925 meters, how long is this going to take? This is going to give Superwoman the information she needs to accelerate down and save the day. Okay, so I can find the time that it takes for this person to fall by taking my equation again, distance divided by speed. Oh, come on. Distance divided by speed. I know the distance is 925 meters divided by the speed of the person, which is 38.9 meters per second. And I'm getting 23.8 seconds. I'm going to leave an extra decimal place in here just for some good measure. 23.8 seconds later from here. Anything past that and it's too late. So that's the time that Superwoman gets here. Notice this is a really complicated question. Now what I know about Superwoman is a number of things. Okay, I know number one, that she's going to fall, or she's going to swoop down a distance of 999 meters. She is starting from rest, and she has a total of 23.8 seconds to get there. .8 seconds. Okay, so now I can use my delta D equals V1 delta T plus a half A delta T squared, right, my favorite equation, to solve for my missing variable acceleration. Right, and I can figure out what the answer is. All right, so let's just write in here my equation. I'm just going to slide this over a little bit. Delta D equals V1 delta T plus 1/2 A delta T squared. Right, and I can solve. I know my delta D. I know V1 is 0, so this whole thing disappears. Plus 1/2 A delta T squared. Notice the nice thing here is I can take my delta T and square it, my 23.8 seconds, divide it by 2, and then take that number and just divide it into my 999, and it will give me A, right, which is my answer. Right, so I'm not gonna do that. I will leave that for you to work on. Okay, and then lastly, I have question 68. All I'm going to do for 68 is draw the picture, and I'm not going to do any of the math here. I'm going to let you try and work through 68. Okay, so 66 was two equations, right? Equation for player A and player B. 67 was two sets of math. Math for the free faller and math for Superwoman. And then question 68 here is two sets of equations again. Now, this one here has a police car sitting at a set of traffic lights. So here's my police car. Notice the key to these questions is in the picture. So here's a police car, right, sitting at a set of lights. Then it says a speeder goes zooming past, right, goes zooming past at 100 kilometers an hour. So here's the cop, V1 is 0, I'm sitting at the light. Here's the second car, constant speed, 100 kilometers per hour. Right. Now we're told the police car was going to have a rate of acceleration, let's make this bigger, of 3.6 meters per second squared. That's a 3. All right, 3.6 meters per second squared. The question is, how long does it take the speeder, how long does it take the cop to catch the speeder? It says, how far does a police car travel when it catches the speeder? Okay, and then C, I'm not even going to worry about. Well, I guess C, it says, when the cop catches to the speeder, how fast will the cop be traveling? Okay, so let's look here just for a minute at my picture. So here goes the speeder, right? Wow, zooming down the road, and the cop goes wee wee, and the cop's going to slowly start to go. After 1 second, the cop's here, the speeder is here. After 2 seconds, I'm just making this up, the cop is here, speeding up, the speeder is now here. After 3 seconds, the cop is here, the speeder is here. They're getting closer because the cop is getting faster, and this guy's not going any faster. He's traveling at constant speed. At some point, the cop is going to be going faster than 100 kilometers an hour, speeding up. I should convert this to meters per second first. I'm not doing it. You're going to do it. Okay, so at some point, the cop is going to be going over 100 kilometers an hour, which means he can now, or she can now, start getting closer to this speeding car, and at some point down the road here, the cop will have sped up so much that the cop will gain on the speeder, and the cop will be right beside the speeder again. So notice that they were side by side at the traffic light, where the cop was sitting, and when the cop catches the other car, they're both in the same place at the same time. Right? That means the delta D for the police car will be equal to the delta D for the speeder, and the delta T for the police car will be the same as the delta T for the speeder. They're in the same place at the same time. So what I now need to do is say, what do I know about the delta D for the speeder? Well, the delta D here is equal to speed times time, because the speeder has constant speed. The delta D for the police officer is going to be, again, I'm going to use my equation that I normally use. Delta D equals V1 delta T plus 1/2 of A times delta T squared. Okay, notice that V1 here is 0, so that means this whole piece disappears. Okay, and I know what the acceleration is. It's 3.6. So delta D is equal to half 3.6, 1.8 delta T squared. Delta D down here is equal to whatever number you've come up with times delta T. But I know that this delta D will be equal to this delta D. So whatever I have on the right side will be equal to this number that I have there. Now I can solve for my one unknown, which is delta T. Once I know what delta t is, I can substitute it either into here or here to solve for delta d. I'll get the same answer either way, and I'll know how far they've traveled, and I'll know how long it took the cop to catch the speeder. Okay. The C part of the question says, when I know what delta D is for the cop and delta T is for the cop and V1 and A, what is V2 for the cop? Right? And convert it into kilometers per hour because it wants to know, does it make sense that the cop should be traveling at that particular speed? Why or why not? Right? So how fast will the cop be going when the cop catches the speeder? So again, I've got two sets of equations. Notice that I have to analyze like we did for the football players, like we did for Superwoman, and like we did for the police car. One object is accelerating while the other has constant speed. One I get to use speed times time, while the other one I get to use my motion, accelerated motion formula. There's a squared in there, I haven't, up there. Okay, so I'm kind of using the same approach for all three questions, even though they're all very, very different questions. So I'm going to stop there. I'm going to try and post both of these videos. I'll post the links in the hub tonight. It's 10:30 now. I told you it would probably be close to 10 o'clock. And then we will, hopefully you'll get a chance to look at them before tomorrow's class. Maybe we'll go through these videos tomorrow together, and then hopefully you'll be in good shape to solve those three problems. If you have any other questions from the bunch here, I will gladly